All right, today what I want to do is continue with our ideas surrounding probability. So the other day I made a video that talked about some different things related to probability. So I'm actually going to start with a problem that would tie into what we talked about in that video. And then we're going to just follow that up with some new material. So let's say I had this example where Ms. Tyson was going to keep a mystery container in her classroom. Then if the students met expectations for behavior, then he or she could draw a slip of paper without looking. All the slips of paper were equal size, so they're all mixed up, and they had the name of the prize written on them. So since they're the same size, they're just likely to draw one piece versus another, so there wasn't any cheating involved. So here's the probabilities of the different prizes they could win. So pencil was 0.40, candy was 0.25, and so on. Well, the first question wants to know, well, why is this a valid probability model? So we mentioned the other day, probability models really should have two things. They should have a sample space, and they should have probabilities that all would work out. In other words, if I looked at all the probabilities, those probabilities should equal 1. So why is this a valid probability model? Well, it has all the prizes listed, so the sample space is there. And secondly, if I were to add up all those different probabilities, so we had 0.4, 0.25, 0.15, another 0.15, and 0.05. If I add all those together, they equal a nice, neat 1. Or think in terms of percentages, if you're thinking about 40%, 25%, and so on, they'd all add up to 100%. So this is a valid probability model. Well, since it's a valid probability model, that means that we can answer some questions related to it. So the first question wants to know, what's the probability that a student won't win extra recess time? So if we look at the extra recess time, the probability that they do win extra recess time is 0.05, or 5%. They want to know what's the probability they won't win extra recess time. Well, I mentioned this at the end of our video last time, but whenever we're looking at a situation where it's not happening, what we're really talking about is what's referred to as the complement. And so if I'm looking at the probability that it will not happen, I'm going to take the probability of 1 minus the probability that it does happen. So in this case, there's a 0.95 probability that they will not get extra recess time. Or maybe you thought about it as, all right, I'm going to eliminate this 0.05 and I add up all the other values. That will give me 0.95. So again, the complement is the not situation. Well, the next question says, what's the probability that a student gets candy or a homework pass? So the probability that they get candy is 0.25. The probability that they get a homework pass is 0.15. So if I want to know what's the probability of getting one or the other, I can add those two together. And so I find out the probability is 0.40. Or maybe another way you think about it is, okay, the candy was this one, the homework pass was this one, let's add up the rest of them. And if you add up the rest of them, I get 0.6. Well, if I took 0.6 away from 1, I'd get 0.40. So that'd be another way to attack it. Now, if you think about drawing one piece or one slip of paper out, and I want to know what's the probability of getting a candy slip or a homework pass slip. The question you ask yourself is, could I get both at the same time? Well, if I cannot get both at the same time, we have a situation that is called a mutually exclusive situation. And part C is an example of mutually exclusive events, because what that means is they have no outcomes in common. So they can never happen together. So mutually exclusive means one of these could happen or the other one could happen, but they can't happen at the same time. All right, well, the nice thing about if I do have a mutually exclusive event, if I'm looking at the probability of A or B happening, and it's mutually exclusive, I can say, well, all I need to do is take the probability of A plus the probability of B. All right, so let's do another example. This example talks about the U.S. Census Bureau, and they kept track of the number of people in U.S. households, and it fit into this probability model. They said, okay, if I had one person in the household, or the probability of having one person in the household was 0.28. Probability of having two people in the household was 0.34, and so on. Well, part A wants to know, what's the probability that the number of people in the household is 4 or fewer? Or in other words, I'm looking at this amount or less. Well, again, a couple ways I can think about this. As I look in the table, though, I've got more values that fit into 4 and less than I do more than 4. So what I would probably do is I'd look at the ones that are more than 4, add those together, and then take it away from 1. So if I look at the ones that were more than 4, we had 0.06, we had 0.02, and we had 0.01. I'm going to take that total away from 1. Or in other words, I'm looking at the complement here. So if I add all those together, I get 0.09. So the probability that I would look at a household that has 4 or fewer would be 0.91. Now, an alternate way of doing that is I could have taken these 4 values and I could have added those together. That would give me the same answer. Part B says, well, suppose we're going to define a household of 4 or more. We're going to define that as being a large household. We want to know what's the probability that the chosen household is large. So now we're thinking about, okay, if they have 4 or more, that's going to be a large household. I'm kind of in the same situation here. I could either focus on the ones that don't fit that category and take it away from 1, or I can just add up the ones that are in that category. Now, this would be considered mutually exclusive because if I have 4 people in the house, I can't have 5 in the house. Or if I have 5, that doesn't mean I have 6 at the same time. So it has to fit in one of those categories. So if it's mutually exclusive, that means I should be able to just add the values together. So 4 or more, if I add all the values together, would end up being my probability. So on this one I have, let's see, 1921.22, that the probability would be considered, or the household we chose would be considered to be large. All right, so one of the key terms we need to keep in mind is what's called mutually exclusive events. And mutually exclusive just means they can't happen at the same time. Now, in section 4.3, there's a couple things that we're going to look at. We're going to look at what's referred to as two-way tables, and we're going to look at Venn diagrams. Well, Venn diagrams you've done before. We'll see how they fit into probabilities in this section. Two-way tables you've probably seen before, but you may not have done any probabilities related to them. Now, before we get into those things, I just did a couple problems where they mentioned the word or. Well, when we look at probabilities and we use the word or, or will mean that we're looking at one or the other. Or we might be looking at both. The example I like to use is if I go to a restaurant and they came to me and they asked me, okay, well, do you want soup or salad? Well, they're probably asking me to choose one or the other. However, if I had a cup of coffee and they said, do you want cream or sugar? Well, it would be an acceptable answer to say both of those things. So when we're thinking in terms of probability, we're really thinking of the cream and sugar situation, where maybe I just choose cream, maybe I just choose sugar, but it's okay if I choose both. So probability-wise, or will mean that. It'll mean we're looking at one or the other, but we might be looking at both. So that's a key part we have to think about as we start looking at what's called a two-way table. If an event is not mutually exclusive, in other words, both of the things can happen at once, one of the ways we can display that is with a two-way table. So here's an example. There was a question on the Census at School survey that asked students if they would prefer to be happy, healthy, rich, or famous. So they had to choose one of those four things. They kept track of the responses based on what gender answered those. So they kept track of the female responses, they kept track of the male responses. So they put this into a two-way table. So the table had the responses across in the rows, and it had the gender down in the columns. All right, well, here's the question. Suppose we choose a student at random from the 218 students. We're going to say event A means that we have a female student. Event B means that we have a student who prefers to be happy. Okay, so anytime they refer to A, they're talking about the probability or looking at getting a female student. Anytime you see B, we're talking about a student who prefers to be happy, no matter if they were male or female. All right, so part A says, well, what's the probability of B happening? In other words, what's the probability that we randomly select someone who chose to be happy? Well, for this problem, I'm not worried about what gender they were. I'm only worried about what they answered. So if they answered that they wanted to be happy, that was 136 people. That was out of all the answers that we got. Well, they said that there were 218 students. So the probability as a fraction would be 136 out of 218. We can make that into a decimal if we want to. That would be 0.62. We can represent that as a percentage if we wanted to. That would be 62%. So if I'm asked to interpret this, basically we're saying that 62% of the people answered happy. Or if I were conducting this survey, I would expect 62% of the people to say they wanted to be happy. All right, well, here's the next one. It says, find the probability that we select a person and they were female and they wanted to be happy. So now things have changed a little bit because it has to be a female. So it has to be one of these answers. They had to say that they were happy. So it's got to be in this happy situation. Well, if we look at this, we had 90 females who said that they wanted to be happy. So I have 90 out of the 218 that I talked to. So if I do 90 divided by 218, I get 0.41. Or there's a 41% probability that we find a female who answered happy. Here's where we have to be careful. The last one wants to know what's the probability of A or B happening. In other words, what's the probability that the person we chose was a female, or the probability that the person we chose wanted to be happy? Well, let's look at the female. First of all, if I just looked at, okay, well, how many females answered the survey? That would be 120. So the probability of A happening is 120 out of 218. Then I think about, okay, how many said they wanted to be happy, regardless if they're a female or male? Well, that's 136 out of 218. And we said that if they're mutually exclusive, all we have to do is add these two together. However, are these two mutually exclusive? Well, we already know that they're not mutually exclusive because we already looked at a situation where females answered they wanted to be happy. So if I think about what I just totaled up, when I totaled up the females, I added up all these values here, the 90, the 20, and the 10. When I added up the happy answers, I added up the 90, the 46. Well, notice one of those numbers I added twice because I added this number, the one that was females who wanted to be happy, I added that one twice. So that means I've got to take those 90 people out of my total because I don't want to add them twice. I only want to include them once. Well, the nice thing is all these fractions have the same denominator, so really I'm going to take 120 plus 136 minus 90, and I find out that the probability of A or B happening is 166 out of 218. Or if we made it a decimal, we're looking at 0.76. So that's where, again, it gets tricky. If it's not mutually exclusive, I'm going to add the two values together, but then I have to subtract out when both of those happen. Or in general, I'm going to use this addition rule. What's the probability of A plus the probability of B minus the probability of A and B happening? And we call that the general addition rule for two events. So if I look at this next example, it says, okay, in a large city, 92% of all residents have a cell phone. 64% have a landline, and 59% have both. We want to know what's the probability that a selected resident has a cell phone or a landline. So this question might be a little bit dated because I'm guessing 64% don't have landlines still, but we'll go with it. So if I'm going to find the probability on this one, first thing I'm going to do is find the probability of them having a cell phone. Then I'm going to add to that the probability that they have a landline. I'm going to take away from that the probability they have both. Well, this one's kind of lined out for me because it says 92% have a cell phone it says 64% have a landline, and it says 59% have both. So my probability here would be whatever 92 plus 64 minus 59 is. And then, 92 plus 64 minus 59 gives me 97% probability that they're going to have a cell phone or a landline. So mutually exclusive, we just add them together. If it's not mutually exclusive, we have to take out that case where both of those are happening. All right, so that's 2A tables. The second part of this, again, is something you're maybe a little more familiar with, and that's a Venn diagram. So some things to remember about Venn diagrams. They're going to consist of one or more circles. They're going to be surrounded by a rectangle. Each circle would then represent an event. Well, the region inside the rectangle really represents the sample space of that chance process. In other words, anything that's possible to happen should be inside of our rectangle. All right, well, let's take that example that we did earlier, and we're going to put it into a Venn diagram. So this is going back to the one that talked about getting a female student, getting a student who prefers to be happy. And we said we're going to call event A, remember, getting a female student, and event B as getting a student who prefers to be happy. So I might label one of these circles with event A, or the female, and event B as the student who wants to be happy. And what we're going to try to do is we're going to try to fill in the Venn diagram with the different probabilities of what can happen here. Now, some reminders where they overlap. Remember, that would be the probability that both of those are happy, that they're female and happy. This area here would be the females who did not answer that they wanted to be happy. This area here would be the people who said they wanted to be happy, but they were not female. And then lastly, some people forget about the area outside. Well, that would be for the ones that were not female and they did not want to be happy. Well, I always start with where they overlap. So let's go back to our data and let's try to figure out, okay, what about the ones that had both female and happy? So I go back to my data. And in our 2A table, the female and happy was 90 out of 218. And I'll come back to that here in a second. We'll put that into a decimal. All right, the next thing that we'll look at. Actually, let's call it good those. So. All right, the next thing we'll look at is the red area that I marked. So I'm going to look at the probability of female and not happy. So let's look at our table and see if we can figure that out. So our female that were not happy, I'm going to erase all this here. So I'm only looking at the female data, and I'm adding up the ones who were not happy. So the not happy would have been 30 out of 218. Okay, the next section would be this green section. This green section would be the probability that they were happy, but not female. So let's look at that from our table. So they were happy, but they were not female. In other words, it's the males. So we had 46 out of 218. And then the outside section, the section I made with the black dot there, that would be the ones that are not happy and not female. Well, I could go back to the table again, but basically I'm talking about whoever's left. So I've already dealt with 90 plus 30 plus 46. So I've already dealt with 166 people. So I'm going to take 166 away from 218, and I find out that's 52 out of 218. All right, so now I'm ready to fill in my Venn diagram. Usually it's going to be a little bit better if we use decimals. So I'm going to do 90 out of 218, see what that is. Well, that's 0.41. So I'm going to go on the middle section. 30 out of 218 is, I rounded up, 0.14. .46 out of 218 is 0.21. And the last one, 52 out of 218 is 0.24. Now, if I really exact all these again, should be my sample space, so they should add up to 1. And when I add them all up, I get a nice neat 1. That would be my Venn diagram. So in the Venn diagram, if we have two circles, you would have two labels. You're going to find the intersection where they overlap. You have the other two areas. And then don't forget, there's always going to be an area outside that we would include as well. All right, so some terms here that goes with this. If I'm looking at the event of A and B happening, that's referred to as the intersection. That means we have all the outcomes that are common to both events. Some notation with that. Intersection might be written this way. A intersects B, or it looks like it has an upside down U. As far as the Venn diagram, that would be talking about this section here, where they overlap. If you're looking at the event of A or B happening, that's called the union. That is going to consist of all the ones that are in A or in B, or they might be in both. How we're going to write that is with a symbol that looks like a U, because it's the union. So if I represented the union, well, it could be in A, it could be in B, or it could be both. So really, the union would be anything inside the circles. Now, we won't use that notation a ton, but you might see it from time to time. So you need to know what the notation is for the intersection, that upside down U, and that's where they cross one another. Or the union, which is looking like a U, and that is where we have one or the other, but it might also be both. All right, a lot of information here, but let's do this last one here. Here's our situation. In one large city, 40% of all households own a dog. 32% own a cat. 18% own both. So if we randomly select a household and record which type of pet is owned by that household, we want to answer these questions. Well, we're going to define D as owning a dog. We're going to define C as owning a cat. So the first one wants to know, what's the probability of D intersect C happening? Or in other words, what's the probability they're going to have a dog and a cat? Well, the nice thing is they told us that. They said right here, 18% own both. That was an easy one. The next one wants to know, what's the probability of D union C? Or what's the probability of owning a dog or a cat? All right, well, this is where we're going to break it down. We're looking at, well, what's the probability of owning a dog? Plus, what's the probability of owning a cat? Minus, what's the probability of both? Well, probability of owning a dog was 40%. Probability of owning a cat was 32%. Probability of both was 18%. So let's see what we're left with. Now if I do 72 minus 18, I find out that there's a 54% chance that I select somebody who has a dog or a cat. We'll tying it all together here. How would I represent that with a Venn diagram? So I'd have a circle that represents the dog, circle that represents cats. I always start from the inside out. So I'm looking at the union of those two things. Well, we said the union, or sorry, not the union, the intersection of those two things. So we said the intersection was 18%. Let me write that for you. All right, then we look at the dog circle. Now we have to keep in mind everything in this dog circle has to add up to the 40% that dealt with dogs. I already have 18% in there though. So I'm going to take 40 minus 18 to get this value in here. And that value there is going to be 0.22 then. Because if I add those two together, I should get the 40 that I need. Everything inside the cat circle should equal 32. Well, I've already got 18 of that. So inside the cat circle, I need a total of 32, which means I'm left with 0.14 here. Now, if you're doing the Venn diagram for real, you wouldn't put those values with the arrows, but you would just put your totals in. So right now, if I look at everything inside the circles, I have 0.22 plus 0.18 plus 0.14. So I've got 0.54 right now, which matches what we had right here. But I want the entire sample space. So I still have to account for what's left if I took that away from 1. So 1 minus 0.54 is 0.46. And that goes on the outside. Because I always want those values always to add up to 1. And that would be my Venn diagram. Well, the nice thing about Venn diagrams is they make it a little bit easier to find our probabilities. So the last question here wants to know, what's the probability that the household owns a dog, but not a cat? So what I'm going to do is I'm going to focus on the circle here that does not include the cats. So I'm going to wipe out the cat circle. And then I focus on the dog circle. Well, in that dog circle, all that's left would be 0.22. So by having the picture of the Venn diagram, I was able to find that percentage or that probability fairly quickly. So I realized a lot of information there today. We'll spend then the next class period or two practicing a lot of these different things. Again, we're just trying to touch on some stuff in probability right now, get you an introduction to that so you'll be at least familiar with, or at least have seen it as you head into future classes.